Hi students, today we are going to look at another interesting lead code problem called flood fill. Let's take a look at the problem statement first. The problem statement says we are given an image which is represented by a matrix and any cell value which is image of ij represents its pixel value. Okay, we are also given three integers which is a point on this grid and a new color it should have. We are supposed to perform a flood fill operation on this starting from the given point. Okay. So how do you perform flood fill? We have to basically change every pixel that is four directionally connected to the current pixel and which has the same color as the given pixel. You have to change them to the new color. Okay. So in this example, all the cells covered in blue have the same value as the first one or the center cell which is the given cell and they are four directionally connected. Hence we change those values. Okay. This one on the other hand is not connected. From here there is no way to reach here. You should reach either via this or either via this. Both of them have a different value. That is why this is not four directionally connected. Hence this remains as 1. Okay. So let's take a look at this solution with an example. So the second example given here is all zeros. Since the given color is also 0, there is nothing to change, so no change is required. So let's go over this example. So initially we are given this point. Okay. Now who are the neighbors of this point? So if you consider this point as x comma y, okay, x comma y, neighbors are x minus 1 comma y, okay, x comma y, y minus 1, okay, x plus 1 comma y and x comma y plus 1. These are all the neighbors of any point x comma y. So we are at this point. So the neighbors will be this one, this one, this one and this one. So let's start. So before going, we have to change the current cell value. So this one becomes 2. Next we start with one of the neighbors. This one has the current cell value which is equal to the old value of the given cell. So this one also becomes 2. Then we have to start tracking its neighbors as well. Who are its neighbors? There is nothing here. They are this one and this one. Now if we take a look at this neighbor, again this cell value matches the old color. So this becomes true. And we have to look at its neighbors. This one is already processed, so there is nothing to look there. This one on the other hand has 0, which is not equal to our old color. So this one remains 0. Okay. Now we are done with processing neighbors of this cell. Now let's go back to processing neighbors of this cell. We have processed one neighbor. The other neighbor is already processed and one more that is remaining is this one. Here again it matches the old color, so this changes to 2 and we continue to process its neighbors. So who are the unprocessed neighbors of it? Only this one. This one again the color matches, so we change it to 2. Okay. Again who are the unprocessed neighbors of this? Only this one. This one again color matches and we change it to 2. Okay. With this we have processed all the cells. This one neighbors of this cell are the only unprocessed one is 0 which doesn't match the old color, so this remains 0. Okay. So we never even reached 1, which is why it remains as is. Okay. So this clearly is a recursive solution. We are recursively going through each and every neighbor of the given cell. So let's try to write solution for this. Okay. So this is what we are given with. First condition is we have to check if given image, okay, is equal to this color or not. Okay, if this is equal, there is nothing to process. If this is not equal, then we have to do some processing. Let's call a helper function fill, okay, which does that processing. So the helper function will have to take the image, the current location, okay, and the current color of the image. Okay. we have to take this current color because we will be overriding this color, right? So to hold that color value, we have to take the current color as well and the new color which needs to be filled. Okay. Once we fill it with that, we just return the image. Now let's try to write this fill function. So in this fill function, what are we doing? So this is the first, let's write the boundary conditions. Okay. If row goes below 0, okay. So for any matrix, right, it's easier to write the boundary conditions and exit at that point to avoid any errors. Okay. So what are the boundary conditions? Row or column should never go less than 0 and row or column should never reach anything equal to its length. Okay. For column, length is basically image of 0 dot length. Okay. So if this happens, that means there is no point to access on this image. So this point is outside this image, which is why we will just return. And the other condition we have is we will process this only if, okay, only if the position, the image at which we are looking is equal to the old color of the cell. The old color of the cell is image of SRC, which is the color in this function. Okay. So if they are not equal, there is nothing to process. We just return, which is the case of 0 in this image. Okay. So these are our boundary conditions. So if the point that we got is outside the image, or if the color we have doesn't match the old color of the cell, which is the number 1 of this highlighted red cell, we just return. If they are equal, what do? We change the color of the cell to new color. Okay. And we have to go through all the neighbors. So who are the neighbors? Neighbors are defined as an array as x. We have discussed that, right? It is x minus 1 0, x y minus 1, x plus 1 0, x y plus 1. So if we take a helper array like this and we can traverse through that, what we can do is, it's just a easier and cleaner way to get all the neighbors. So we know that neighbors always come from by subtracting or adding these values to the current cell value. So we know the current cell value as row and column. So we just do, for each of those points, we add that value to get the new value. Okay. So the other way to do this is just calling this function 4 times, but this one is a much cleaner approach. Okay. So we are again traversing the same function for every neighbor, and whenever the color matches, we'll change the color. Okay, let's try to run this problem and see. Yeah, let's submit it. Yeah, so there we have it. This is our recursive solution. What are we doing? We are starting at the given point, and if the color matches, we are changing the color. Okay, and for every neighbor, we are repeating the same thing as long as we reach somewhere outside the image. Okay, so now what is the time complexity of this solution? So time complexity is, in the worst case, we'll traverse the entire array, double dimensional array. Our array is of m by n size, so the time complexity would be m by n. Okay. Similarly, space complexity will also be m by n because we'll have those many call stacks. Though we are not explicitly declaring anything, every time we call this function, right, it creates that extra call stack. So in recursive functions, that will lead to that much of memory. Okay. Yeah. That's all we have for today. If you have any questions, please leave a comment on the video. If you like the video, please like, share and subscribe. Happy coding. Thank you.